Welcome to the Global Composite Express webinar series. My name is Wenping Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched Composite Design and Manufacturing Hub with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. And we envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. Composite Design and Manufacturing Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. You are welcome to join the global composite community at cdmhub.org. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by our sponsors from Dassault Systems and Cytec Solvay and Anna Swift. We greatly appreciate their financial support for CDM Hub. We also invite more organizations to join them and to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. We'll email you once the recorded video is available online. The presentation will last around 45 minutes, and we will have about 10 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. For the sake of time, after the presentation, questions may be summarized and rephrased for the speaker to answer effectively. All your questions will be sent to the speaker for him to answer at his discretion. Next, let me ask Professor Byron Pipes to introduce our distinguished speaker today.
It gives me a great deal of pleasure to introduce Professor Stephen Nutt. Stephen joined the faculty of the University of Southern California in 1994 as professor of material science. He founded the M.C. Gill Composite Center in 1996 and has served as director of the center to the present date, almost 3 decades. Within the Viterbi School of Engineering, he has served as Senior Associate Dean for Research, the chair of the Mauch Family Department of Chemical Engineering and Materials Science. He serves as co-director of CIMA, the Center for Electron Microscopy and Microanalysis. Dr. Nutt's research group focuses on processing science for fiber-reinforced composites, including experimental determination of mechanisms, resin flow, air removal, compaction, and the like, and the underlying scientific principles governing the production of composite laminates and composite structures. Hallmarks of the group include the in situ process diagnostics, design, build, and instrumented test beds, coupling with the process modeling. The scope of the research encompasses composites for aerospace, wind energy, and automotive applications, and emphasizes prepregs and liquid molding processes. Additional topics include high temperature phenomena in composites, such as aging effects on mechanical performance, processing of ceramic composites, and interface design. His project support comes from industrial sponsors, about 2/3 of his support, as well as from federal agencies such as the National Science Foundation, NASA, and the Department of Defense. I'm delighted to turn the floor to Professor Stephen Nutt.
Thank you, Byron. It's an honor to be selected for this seminar series, and I hope you'll enjoy the presentation I'm about to give. We've been working on prepregs for probably 15 years, and I'm going to give you a sort of a tour through some of the highlights of the past decade or so. I'm going to be talking about out-of-autoclave prepregs, sometimes called vacuum bag only, VBO prepregs. Is probably a more apt descriptor. Anyway, let's just a brief overview on first why we're doing this and why we're interested in alternatives to autoclaves, and some of the present designs for commercial prepregs and some of the limitations of those, and then introduce a term that you may or may not be familiar with, semi-pregs, and the motivation for semi-pregs through thickness permeability and restoring robustness to the processing. And then we'll also talk about some consumable materials that are fairly new, that are really vital to the success of the semi-pregs. And then we'll talk a little bit about some of the efforts to optimize and sort of move towards insertion into practice. You're all familiar with this well-traveled graphic of the Boeing 787. It's a largely composite commercial airplane, the first of its kind. It's been followed by the Airbus A350, similar composite aircraft. And as you're familiar with aerospace, they generally project sort of the worldwide fleet 20 years in advance. And the 787 is what's classified as a wide body, and you can see the production volumes there are scheduled to double in 20 years, but they're far fewer than the single-aisle aircraft. And therein lies a little bit of a challenge, is how to meet the production rates required for single-aisle aircraft using composite materials. And it's pretty clear that alternatives to autoclave are going to be absolutely essential to meet those production volumes, if at all possible. No. So there's one of the motivations for autoclave alternatives. Aerospace presently is driving the demand, at least for carbon fiber composites, and the production rates are going to have to increase if the paradigm for the 787 and the A350, if that is going to translate to single-aisle aircraft, which have to be produced in much greater rates. Biggest autoclave in the world. Yeah, it's pretty darn impressive. It's in Everett, Washington. And autoclaves, as you're probably aware, have high capital costs and high recurring costs. Typically, nitrogen gas is used in the autoclaves, so they're expensive. And the reason, though, that they're used is underlined in the last bullet point, is because it imparts robustness to the process, meaning you can produce high quality parts consistently, even if your methods are maybe a little bit errant. The other limitation to autoclaves, and I touched on this in the previous slide, is it constitutes a bottleneck. And the throughput, particularly for large autoclaves, is very slow. And thus, to increase production rates, we have to either go through the autoclave faster or go around it. And going around it is basically the avenue that I'm going to talk about, and that is oven cured. Ovens are far cheaper to produce and to operate. The caveat is that they're less robust. We only have atmospheric pressure and the difference between that and the vacuum. So there's a much smaller pressure gradient, and that really removes that robustness from the process. All right, let's move on to the current state, present state of technology, commercial autoclave prepregs. Start with very simple schematic of a bubble in a resin, where the resin pressure is roughly equal to the so-called vacuum bag pressure. We have gas somewhere in that assembly that's trapped, and we only have a compaction pressure of the difference between atmosphere and then the bag vacuum pressure. And if the pressure inside the bubble exceeds the resin pressure, then the voids are going to grow. That's pretty simple. However, if we apply autoclave pressure, then we can control and even shrink the pores in the assembly. So that's really a very simple picture of what goes on inside the vacuum bag and the composite laminate. And that's with now, if we look at commercial prepregs, out-of-autoclave prepregs, they are designed with dry fibers in the mid-plane of the prepreg. And the strategy is to remove gas via what we call edge-breathing dams. And thus the gas is removed to the periphery of the laminate. And you can see in the top part of this figure, the little cartoon shows resin films applied to the fiber bed, partially impregnated. And then you can see the image, the cross section of impregnated fibers plus dry fibers, which we sometimes refer to as evacuated vacuum channels, EVACs, and then the whole bag assembly that is in the part B of that figure. If any of you have done this, you kind of know the ingredients there. The key for out-of-autoclave prepregs is the edge-breathing dam on the edges. Okay, that it allows the gas to escape and the consolidation to be achieved. All right, that's the current state of art. Let's look at some limitations. This is a work from Centilla and Hubert that basically looked at void content as a function of vacuum quality. And then the important thing to take away from that graphic is the increase in porosity when the air evacuation is restricted. Those are the bars on the right. So that can be either your edge-breathing dam not working properly, or it can be a corner in your laminate, ply drop, any number of things. Then we move to another limitation, and that is volatiles. And the primary volatile of interest today is moisture, water. In older generation prepregs, they were often solvated, but and there's still quite a few shops that use solvated prepreg, as we learned in a recent project, because of qualification and certification. Anyway, what you see is as this is actually the red curve there is based on some calculations due to a model from Cardos, but it just shows that voids are going to grow when the initial relative humidity is being absorbed into the prepreg, at least when you cure out of autoclave. However, when you cure in an autoclave, voids will not grow. That's consistent with the previous graphic that I showed. And this is a final limitation here, showing what we call flow limitation. Prepregs, as you know, have a finite outlife, typically on the order of 3 or 4 weeks. And then they basically gradually lose the ability to flow. And what we see here is a series of micrographs of polished sections from prepreg that's been left out for a number of days. a week, 2 weeks, 3 weeks, 4 weeks, etc. And you can see the porosity gradually growing as the flow becomes restricted due to increased downtime. Okay. Okay. Now, there's also some scale and geometric challenges. What's shown here is breathe out distance. And you can think of this as just your laminate size. If you're making an airplane wing versus making a square foot panel, your breathe out distances are going to be quite different. And as the distance from the vacuum source grows, the evacuation pathway and the vacuum hold times increase as the distance squared. So this basically slows down the whole process of making laminates as they get larger because of these long breathe out distances. And that of course slows down production rates. Another challenge, a frequently encountered feature is what I call ply drops, sometimes called ramps, where the laminate has to change thickness by design. And that leaves terminated plies in the stack with no egress pathway. All right, that's another problem. And then, of course, corners, both convex and concave. And you can see some of the problems, particularly with convex corners because of fiber bridging and loss of pressure. You get increase in cavities. All right, let's turn then to what we call semi-pregs in this section. First, we'll start with sort of conventional prepreg, commercial prepreg for out-of-autoclave. 2 resin films sandwiched on a fiber bed and partially impregnated. The center plane left dry to facilitate air removal to the edges. And what we've thought is a fairly simple idea is to increase vacuum bag only process robustness by facilitating air evacuation, by promoting Z permeability. And so instead of removing gases via the edges, we're going to try and remove gases in the Z direction. And we do this by disrupting the continuity of the resin layers and replacing the continuous films with discontinuous resin. And you can see the little cartoon there on the bottom summarizes this. Of course, the egress pathways now are orders of magnitude shorter, and there's redundancy in these pathways. There's multiple pathways for air removal. This all makes sense, but can we do it? Well, the first attempts we undertook are shown here, where we're basically relying on topography in the fiber bed and basically coating resin onto the raised sections of the fiber bed. This is a 2x2 twill. And then we measured Z permeability and the so-called USC preg, the red dots there correspond to the cartoon at the left. And of course, we get several orders of magnitude increase in Z permeability, even as the ply numbers increase. Now, in this particular approach, the resin pattern depends on the fabric texture and topography, order of magnitude increase in Z permeability. Okay, that's good, potentially. Then what about what effect will this have on the process robustness? Well, we looked at, used as our sort of benchmark, a conventional prepreg and one-sided out-of-autoclave prepregs. And we then basically introduced a number of variants in the process that made the curing more challenging. And The so-called USC preg in red there is the semi-preg that I just described in the previous slide. The first thing we did is remove the vacuum hold that's commonly recommended for commercial VBO prepregs, and no porosity in the semi-preg, in the USC preg. We sealed the edges, so non-breathing edges. Again, no porosity. We conditioned with humidity, almost no porosity, and we embedded ply drops, again, no porosity. So all of these are what we call non-ideal process conditions, and virtually no porosity with this semi-preg. All right, here we continue with some polished sections. This shows the control and the kind of pores that we're seeing in conventional commercial out-of-autoclave prepreg, one-sided, and then the USC preg, which we've since dropped that name. We just that was my student's term that she came up with. Anyway, you can see that their porosity has been completely eliminated in the semi-preg, and this shows the same graphic from the previous slide. All right, so these were all fabrics, as you can see here. And the question we next addressed was, well, would this paradigm extend to unidirectional prepregs as well? Because, in most commercial aircraft parts are made with UD tapes. So we did some, we didn't have a really good way of doing this. So basically we made some UD semi-preg, as shown here. It was a little bit tedious, our approach, but we were just trying to demonstrate proof of concept. Same story here. We basically greatly reduced porosity in our semi-preg, and increased the robustness of the process in doing so. However, there are limitations that we encountered, and they're shown here. Basically, resin-starved regions, and also when the resin strips were a little bit too wide, we ran into some gas entrapment, and we basically, if the strips were too far apart, we ran into some flow limitations. So we needed to fine-tune this little initial experiment, which we've since done. Now we get to the consumables, which is an often overlooked sort of aspect of the whole process. But about the time we were finishing up our work here on these semi-pregs, we learned about the semi-permeable membranes that were available, and we thought, aha, this may be the missing link here that we really need. So we'll go back to history and look. There was actually some excellent work done at Boeing a long time ago that's often overlooked because it's not in a journal. It's in a textbook, but they basically studied sort of the physics of prepreg consolidation and invoked some mechanical analogs. And those of you who are mechanical engineers are really familiar with this. This is spring and dashpot type of model. And they basically compared the prepreg to a spring and a fluid-filled dashpot. And then they followed what happened during the consolidation of the prepreg. So you can see here that in step one, we have no applied pressure. This is the mechanical analog. And step two, we apply pressure, but it's carried by the resin, not by the fibers. And then we open the valve in step three and allow compaction to begin. And in this case, resin was allowed to bleed. And so then as the piston sort of dropped here, then the load began to be shared by the fibers and the resin. And equally shared. And then finally, most of the load is being carried by the fiber bed, as the resin is in this case lost by bleeding until finally it's all carried by the fiber bed. Anyway, so this actually is a really important graphic that I make all of my students study and understand. And if we can then apply this to the fully impregnated case, the resin can carry the pressure if the edges are sealed, or it can bleed if a pathway exists. In semi-impregnated prepreg, the resin has to flow to fill the dry spots. Initially, the fiber bed will carry some load, but in latter stages, the resin can carry the pressure if it's sealed, or bleed away if the pathway exists. So let me introduce semi-permeable membranes. Some of you may not be familiar with this. This is a commercial product that AirTech sells. This is not a really good section of it, but basically it's a plain weave nylon fabric, which is just a carrier. And then there's this Teflon semi-permeable membrane, meaning it's permeable to gas, but impermeable to fluid, to liquid, which is exactly what we would want, to cover our laminates of semi-preg. So basically, this will allow gas transport in the Z direction, but not resin flow. So now we're going to show some process monitoring using some. I'll have to explain what you're looking at here. This is the cure schedule on the left that basically has an intermediate temperature dwell to allow resin flow and saturation of the fiber bed. What you're seeing on the right is basically a transparent tool plate, okay, in an oven. And what you're going to see next is what happens as a function of time. Okay, and so these little bubbles, I'll show it one more time because it goes by pretty quickly. And then the final ramp up is to the cure. Okay, and this is sort of our benchmark, our conventional out-of-autoclave prepreg. I'll show it one more time. Okay, there's the initial ramp. You can see a little bit of flow. There's the dwell. Okay, a lot of gas trapped at the little nodes where the toes overlap. And then the final ramp up, not much changing, and that's porosity. Okay, now let's look at semi-preg, where we have through thickness permeability to increase gas evacuation. We have saturation, we have dwell, everything looks good, but not so good. During that dwell, we're seeing some gas emerge at the tool plate. We're not quite sure what this is from, but we can hypothesize that there's low resin pressure and perhaps some volatile evolution, volatiles being primarily moisture in this case. All right. Now let's do the same experiment, though, with a semi-permeable membrane on top to facilitate gas egress. Now, this video is going to shake a little bit. It's not an earthquake. It's just some instability in our little setup. But anyway, here we go. Then we get saturation. Everything looks good, but will it stay good is the question. Fingers crossed. Voila. Yeah, success. Okay. Basically, we think what we've done is we've achieved air removal at the bag side surface using these resin impermeable consumables, but gas permeable consumables. And we think that we've maintained higher resin pressure. That's to be determined. And so I tasked the student with trying to measure the resin pressure during the cure. And that turned out to be a much more challenging task than either of us realized. But this is the little setup. You can see it's basically a sort of a hypodermic little syringe type thing and embedded in the laminate. All right. And this is the results of the resin pressure measurements. And you see at the top, this is the top of the vacuum bag and the tool surface. So this is the temperature, and the bottom is the pressure. And with the semi-permeable membrane, those iterations are shown in green. And you can see multiple stages here. The takeaway, it's a little bit noisy, but the takeaway is the resin pressure, with the semi-permeable membrane maintains a higher pressure level than with conventional consumables. So what we have is a peak, and that's when the resin flow begins into the dry regions, and we're going to get resin pressure drop when that happens, and that in fact does happen. Get resin bleed, and then when we have so-called bleed conditions, we do get void growth. All right, so we think we've proved our hypothesis, and now we're left with some more practical considerations. Well, how do we design these semi-pregs? Because there's many different options, and some of which are shown here. We all discontinuous resin patterns. There's stripes on the left, there's islands in the center, and there's a grid pattern on the right. And then, of course, with each of those, there are variables of dimensions and spacings, et cetera. And it's a little dizzying how many options there are here. These are a few of the options that we've explored with different hole sizes. And we can also, of course, vary the spacing, the coverage, et cetera, et cetera. But anyway, distill this into a few simple points. We want to balance the need for maximizing dry surface area to maximize permeability, and while minimizing resin flow distance to mitigate resin starvation. So we have to figure out what is the Goldilocks condition for those two constraints. Well, we figured this was going to be way too difficult to undertake experimentally, because there are just too many knobs to turn. And so we undertook a little bit of a modeling approach, and the models are shown here: stripes, islands, grids. And then we started looking at some of the analysis, where we looked at so-called the percentage of sealed interfaces, as well as the tortuosity of the Z pathway for egress. And as these the area coverage increased, and then we're looking at the different patterns and different parameters here to develop kind of a simple process map, where we look at the effect of the percentage of sealed interfaces and the tortuosity of the egress pathway. And we can basically divide this on the midplane where of this graph, where the permeability is sufficiently high above the midplane, and it's dangerously low below that. It's limited in utility, but at least gives some guide to how one would go about designing these prepregs. Basically, permeability is going to increase as the dry fiber surface area increases and the sealed interfaces decrease, and the tortuosity path decreases. All right. We then looked at the sizes of openings in the grid patterns, and as the diameters increase the time to evacuate decreased. Here shows some of the trial semi-pregs that we made, and dry feature size increasing decreases the evacuation time. Then we looked at flow distance, and we have heating rates here, and 3 different heating rates, and our model shows this is for the UD prepreg and the stripe pattern of resin. See 3 different temperatures here, and resin flowing from the stripes in to cover the dry pattern. As the dry feature size increased, the evacuation time decreased, but we recognize that there was a risk there that it's the width of the dry features was too wide, that the resin wouldn't sufficiently flow during the cure cycle. Well, another variable, of course, is fiber bed. We all know there's multiple fabrics, fiber types, and even spread toe variants here. Basically, on the left, we show the results of continuous resin out-of-autoclave prepreg, and on the right, the semi-preg. It all looks like a good story. And what we found is basically that for a variety of fiber formats and materials, aerial weights, that our semi-preg approach was effective. However, there are some limitations to this approach, particularly very heavy fabrics, and perhaps non-crimp fabrics and things like that. Well, this is something we don't often get to address in academic research, but we tried to at least indicate pathways for scale up. We know that it's one thing to make small laminates in a lab. It's quite another thing to make an airplane. We really, methods that we were using really had no pattern control. They were very labor intensive, and we were making prepreg sheet by sheet. We realized this was never going to make it out of the lab unless there was a pathway to making, to actually producing at larger scale. And this is one of the approaches that we looked at. This is something we call de-wetting, where we take a resin film, and this is shown heated. This is in real time here, and these are seconds. And basically, we can de-wet resin films and form discontinuous patterns fairly easily. Ideally, we'd like to control the resin distribution, integrate steps, and fabricate continuous rolls. There are 3 approaches that I'm going to describe. The first of these is de-wetting. We've done this at the lab scale. We think that this can be made adapted into a continuous process, and we can control the resin pattern by introducing nucleation sites. And we think one advantage of this approach is potentially backwards compatible with existing prepregging machines. Anyway, that's one approach that's on the table, so to speak. Another obvious approach, I think, is what we call gravure printing, which is as old as the printing press, maybe even older. It's shown schematically on the left here. The advantages is that it's a continuous process, and you can control the resin pattern via the geometry of the roller. You can see this is just a device for transferring resin from a bath via the roller to a backing paper to form a discontinuous pattern. Challenges, with epoxy, you're always worried about latency and advancing cure, out time, etc. And the last approach is really quite different, and that's resin droplet deposition. And this is an interesting one. It's one that I'm kind of partial to. The advantage is that it's very flexible. You can basically spray resin onto a moving fiber bed, so it can be continuous, or you can move the nozzle, which allows you to control the pattern and the areas covered. And we can either do this via a spray or by single droplet, and they both have merits and disadvantages. All right. Well, a low degree of impregnation is a disadvantage, of course. But what I'm going to show here is a proof of concept. And imagine that this brown paper here is a fiber bed. And this is just a little gantry system with a little deposition gun here. Watch this. All right, so what have we made there? Well, we've made a pattern of droplets, resin droplets, and we can control this pattern very precisely, the size of the droplets even, spacing, yes, all those things, so the areal weight of the resin, all can be controlled. In fact, we can tailor this to specific fabrics. Anyway, this is actually pretty cool, and it sort of opens the door to the possibility of what I would call making prepreg on demand. You notice that gantry system there. If you've ever been at a CAMEX exposition, you know that they often show cutting tables. You know, Gerber and Eastman and so forth have cutting tables, which have almost identical gantries. Okay, so think about that for a while and see what you come up with. Whoops. Okay, I will finish up here with some concluding remarks. We think we have a good case that by redesigning prepreg, we can restore robustness to prepregs that was lost when one left the autoclave behind. And key here is like combining some of the prepreg format design with use of consumables. There's a lot of work to be done, I think, remaining to optimize the materials for specific fabrics and resins as well. And a major challenge for anyone trying to enter the prepreg business is the cost of entry for a prepregging system. But that droplet deposition approach, I think that challenge might be addressed. These are the people that do all the work in my group. Happy day, I must have been fed recently. And these are some of the papers that we've written on this topic. And they're all available at the link on the lower right. Thank you.
Professor Nutt, thank you very much for your presentation. We've enjoyed this, and it's my privilege now to field some questions. So a reminder to the audience, please put your questions into the Q&A box, and I'll ask those here to our speaker, and we'll entertain questions for the next little while. So just beginning with this, some questions initially, as you were talking, people asked a couple questions around storage. And with the semi-pregs, are there issues you need to be aware of during storage, such as perhaps capillary effects causing flow and so on beyond what you intended?
Well, there's always an issue with storage of epoxies, of course, because of the limited shelf life and limited out time. I don't think those are any worse with semi-preg, and these I think one drawback to our approaches so far is our initial degree of impregnation is almost zero. Whereas conventional or commercial out-of-autoclave prepregs have maybe 40% impregnation. And that has some advantages, particularly, in practice for things like what they call rework. You have to pull a prepreg ply up from a stack and put it back down again. That is going to cause some challenges with semi-preg, in which the resin has no degree of impregnation. There's going to be resin transfer to various things. So I don't think storage per se is an issue. There are some practical issues, I think, with this semi-preg approach that are it's not going to be able to use exactly the same practices all the time that you've used with conventional prepreg. I hope that's enough of an answer. Oh, but with storage, that's an entree into what I really wanted to say. With the droplet deposition, the approach the third one that I described there is potential, I think, to contemplate not storing prepreg at all, but making prepreg as you need it, and actually combining the droplet deposition to make the prepreg with the cutting table that cuts the kits, and I think that's just a tantalizing proposition that you could really solve multiple problems. If that paradigm could be executed in practice, that's a big if. I realize that. But I'm not the only person advocating for this, by the way. I've run into a couple of other people that would love to eliminate freezer storage.
Mm-hmm.
Yeah.
Freezers and autoclaves.
Yeah. But yeah, good question. It really sort of opened up, several things that I only briefly touched on in the presentation.
We've got another question around semi-preg, around the requirements for resins. Are there particular requirements? And a follow-on question was that kind of using temperature to slow things down, beta staging and so on. But maybe before those detailed questions, what are the general requirements for resin? Is anything on the table, or are there specific restrictions and constraints to take care of?
I guess the honest answer is I don't really know of any constraints. I'll disclose that the resins that we've been using are aerospace epoxies. They're the same types of materials that are used for conventional prepregs. So we don't know of any limitations per se. One thing that question opens up is most prepregs are quote unquote B staged, and we really haven't B staged our materials, at least not intentionally, in our processes.
And is part of when you showed the diagram about trapping air, and you had different layers stacked on top of each other and making sure you had a pathway out. Are there any consideration about with your tailoring method, the deposition gun? Is any thoughts about tailoring the grid pattern based on the orientation the ply may be in a certain stacking sequence?
Yeah. Well, yeah, you're getting ahead of us there a little bit. Yeah. We haven't really pursued that. That's I think something to think about. I guess I would say that thus far we really haven't paid close attention to sort of matching, sequential plies in strategic ways, and it really hasn't made a difference. So our intuition is that, well, once an egress pathway is kind of established, it kind of stays semi stable until the gas is removed. At least that's what it seems to happen in practice. Not a lot of direct evidence to support that, but I think there is opportunity, and particularly with fabrics like spread toe, where you might want to strategically adjust your resin pattern to sort of take advantage of pinholes and things like that. With the spread toe, you're really spacing out the pinholes a lot farther than in conventional fabrics. So I guess the answer to your question, no, we haven't really thought about trying to match up our patterns. That really increases the degree of difficulty, I think, at least from the fabrication shops. If they have to sit there and position each ply to the millimeter. That's going to be tough.
Yeah. Back to the another question here about resin. Someone raising the question: thermoplastics, thermosets. Any thoughts on thermoplastics?
We have not yet looked at thermoplastic. That's a really good question. We haven't really been tasked with doing that. We haven't had a response, but possibly. I just. I guess we can certainly make the semi-preg with thermoplastic resin quite readily. That's no problem. I would imagine that it would be equally effective at gas removal, but we haven't tried it.
Well, someone's taking this even a step further, asking about using semi-pregs, for example, in droplet deposition slurries for ceramic matrix composites. Any thoughts there?
Yeah. Well, one thing, I'll take this in steps. We know that our little droplet gun will work with thermoplastics. In fact, that's what it was originally designed to do, and we've done it with thermoplastics. But for ceramic composites, it's a different problem with ceramic composites. You're trying to densify. You're trying to remove gas. That's true, and eliminate porosity. But you're often trying to fuse particles together, as opposed to really curing things. Well, I guess it all depends on the ceramic composite system, doesn't it? Because carbon starts with conventional prepregs. I'm getting off topic here. I haven't really thought yet about semi-pregs for ceramic composites, but I just, in the so-called PIT processing, the polymer infiltration and pyrolysis, you're typically creating pores, and even if you fill them originally with resin. I'm sorry, I'm just sort of wandering with that question because I'm a little bit baffled about how to think about it. But I would say we haven't really thought about using this for approach for ceramic composites, but there might be some utility. Yeah.
Always get interesting ideas in the Q&A. Yeah. Some other questions around challenges with the additional bulk of these out-of-autoclave prepregs, particularly around corners.
That's someone who has some practice. Yeah, that person asking that question. Yeah. That is a really big bulk factor. Is really what the question is aimed at. And yes, the bulk factor is higher when you have resin sitting on the fabric, surface as opposed to partly impregnated. It's even an issue with commercial out-of-autoclave prepregs, I am told. We don't make a lot of corner parts in our shop, our little lab here. One of my former students works at Lockheed and uses out-of-autoclave prepreg, and he says the bulk factor is a huge problem around corners specifically. So it's a topic for another student, I think. Corners are problematic for fabrics in general, right? I mean, they particularly concave corners. They just don't want to conform to those sharp changes in geometry. It's a little bit more difficult when the bulk factor is higher like this. I think that might be an interesting topic, for maybe a master's student or something like that to investigate, to see basically how could that challenge be addressed. You really nailed a significant problem with out-of-autoclave prepregs in general. I guess my impression is there's not going to be a silver bullet here for it's going to solve all the problems, and we're going to have to sort of address them systematically and hope to learn new things in doing so. Yeah, good question though.
Someone asked a follow up as far as are there any issues as far as sliding between layers? Does semi-preg offer additional resistance to interlayer slip?
We haven't seen it, but admittedly, we haven't made a lot of contoured parts with this. So sliding is more of an issue when you have contours. And I'll tell a little bit of an anecdote. When I went and saw the Boeing assembly plant at Everett, this is huge space where they assemble aircraft. And I turned to my postdoc at the time and I said, I don't know why they would even listen to us, because we make these little, tiny little lab scale samples, and then just seeing the contrast in the scale of what they were doing there at the assembly plant, I thought, wow, it really made me aware of just the disparity in scales, and something that we all need to keep in mind, I think, because we're all going to be working in labs with little things, and there's a legitimate question as to how well our findings scale to industrial scale. I'm sorry, what was that question again?
Sliding.
Yeah, we haven't really seen that much, but perhaps there might be some challenges there. Yeah.
Maybe we'll move from the processing room for a second. A couple questions around things like fiber volume fraction, resin content. Are we talking similar fiber volume fraction or resin content in a cured prepreg as opposed to traditional prepregs once you've cured the system?
I have to thank the person for that question, because it's a simple answer, and the answer is yes. In fact, we're targeting exactly the low 30s, 32-33% resin content to be to do fair comparisons with commercial prepregs. So yes, same resin content, exactly. Yeah.
And then the follow-on question someone has: how do mechanical properties compare? And I'd expect if you get similar fiber volume fraction, a lot of things are going to be very similar. But that's
yeah. I don't even have to answer that question, Jonathan, because you did. That's the good news is that we see no difference in mechanicals. We really didn't expect any, because, like as you said, if we have the same resin content and even lower porosity, exactly. No sacrifice in mechanicals. I think there's some legitimate questions about how well will this sort of paradigm, insert into practice? And some concerns people have about, some parts require what they call rework, where, the technicians have to pull up, apply. That's going to be a mess. When you have near zero impregnation resin on the surface, that resin's just going to go all over the place. But we in a related project, we've been doing automated layup, pick and place robots to pick up plies and position them onto tools, and then using roller compaction with a robotic arm. And even for demonstrator parts and C channels and saddle contours, no rework required, and we think comparable quality to manual hand layup. But the project's not over yet. We'll know in a few months. But I think, there are ways to make these approaches practical and scale them up. I should give a shout out to one of my former students who's actually launching a startup company to make this prepreg, and he has purchased a prepregging machine and will be delivered later this month. And so I'm kind of excited to see if this will actually work in practice.
Absolutely. Well, thank you very much, and thank you for the presentation, for the questions and answers. There are a few questions we didn't get to, and so to those that ask questions, we will send these again to Professor Nutt for him to respond to it at his convenience. And again, we thank Professor Nutt, our speaker, and remind you all of the upcoming webinar here in another few weeks from Dr. Frank Henning. And again, this will be recorded and made available on cdmhub.org, and we'll send you an email as that's available. So again, we thank you, Professor Nutt, thank you to the audience, and look forward to seeing you again here in another few weeks. Thank you all.